Okay, welcome back. Please take your seats. So I asked our tutors to give us an essential summary of what they presented. Since two of our tutors are leaving a little bit early, I thought it would be best to do this now while everybody's here and everybody's still fresh. And so Brendan's going to start, and then Corin is going to speak after him, and Ewan after. And of course, we'll close the day with Michelle, but she will come back and do some of the things.
Hi everyone. So I have a one-slide summary and just a few minutes summary of what I spoke about on Tuesday, which I hope some of you found useful. So I do most of my work on Bayesian statistics, which is what I talked about on Tuesday, and the basic idea of that is this understanding that the mathematical tools of probability theory, or the mathematics of probability theory, you're allowed to use that to describe certainty and uncertainty and degrees of implication. So how strongly does my data set, or the statement that my data equal this set of numbers, how strongly does that imply that my conclusion should be this, versus how strongly does it imply that my conclusion should be something else? And that's the kind of fundamental idea of Bayesian statistics, is that you use probability theory to do that. I also spent a bit of time just introducing you to the idea of probability distributions, which are everywhere. In Bayesian statistics, you're pretty much always using probability distributions, and I thought some people may not have learned those explicitly before, so I spent a little bit of time covering those. Okay. So this is very frequently used in astronomy, and as we've come to hear from the other speakers, in some cases it's very difficult to build a model that, or to do explicitly a Bayesian analysis of a data set, say, if you're in a really huge situation. So I like to think of Bayesian statistics as being most useful if you're in the kind of high noise to signal regime, and if you're working on small data. And that's not because I think there's anything wrong with the foundational ideas, it's just because in practice it's very hard to apply once things get beyond a certain level of complexity. So it's a useful thing to know how to do, but it won't solve all of your problems. So in science, we're often interested in things that are kind of on the borderline between being known and being unknown. So there's always uncertainty, and that kind of gives the reason for why Bayesian statistics has a lot of applications. Because you'll get some data, hopefully, if it was a well-defined, well-built experiment or set of observations that you took, hopefully the data set will answer a lot of questions that you had in mind, but it will never answer all the questions you might have in mind. And one of the reasons is that when you get your data, you'll say, oh, well, that resolves this, but it doesn't resolve this other thing. So there's still uncertainty about something. And if you want to describe that, if you want to put error bars on any parameter estimates and put them in the abstract of your paper, basically the correct way to do that is to calculate the posterior distribution for whatever your parameter you're trying to estimate, and then summarizing that posterior distribution in the abstract of your paper to describe how much uncertainty you think there is given the data set that you have. I then gave a description of the Metropolis algorithm and a Python code which implements the Metropolis algorithm. And the reason I gave that one is that it's probably the most general and easy to understand algorithm for doing Bayesian computation, which is the topic of how do you describe and summarize posterior distributions when you're in high dimensions. So if you understand the Metropolis algorithm, you kind of understand the foundations of MCMC, kind of 3/4 of what MCMC is about. And then, of course, there's a whole literature of other more complicated methods, but a lot of them are based on the Metropolis algorithm or closely related to it. I didn't get to nested sampling, but feel free to take a look through my slides and or my writings or anyone else's writings about nested sampling. That's another general method that is useful for both calculating the posterior distribution, so the same thing that the Metropolis algorithm is meant for, and also for calculating marginal likelihood, which is this number, and I didn't get into this either. It's this number that kind of measures the quality of your model assumptions as a whole. So it's instead of describing how good the fit is at the best fit values of the parameters or at a certain position in parameter space, it describes the fit of the model overall, taking into account all the possible values of the parameters that you thought might have been the case. And so these are two algorithms that, again, don't cover everything, but if I was going to teach you, well, I was going to teach you two algorithms, and I only got through one, and I thought, well, these two things they cover a fairly wide range of territory, so I think they're worth knowing. So I'll finish there, and thank you for having me, and thank you to the organizers, and thanks to everyone who went to dinner with us and all that stuff. I had a good time, and now I know not to order the fish for anyone who was there last night. Okay.
All right, thank you very much.
So I just have about 27 slides. No, just the one. Okay. So yeah, just a quick summary, really, of the main points I said, and everything I said about parallaxes and Gaia was really just a cover for trying to say something about statistics. So what I've tried to summarize here, and this was also the kind of the purpose of the sort of technical note that I sent around last night. But this is the short version, is just to sort of summarize some of what I see as some of the key points in inference. And this is kind of regardless of whether you're doing machine learning or statistics, but as Michelle said, the division between the two is somewhat artificial. This may sound very obvious, but I remember when I was in school trying to solve maths problems, my teacher would say, well, before you try to solve the problem, make sure you've understood the question, right? Because that really is half the battle. So really make sure you define your problem clearly. Often when I talk to people and we sort of get into a bit of a mess about what's going on, it's because we have a different understanding of what the problem is. So really make sure you clearly define the problem. And then understand your data. Yeah? We didn't talk much about visualization, but this is really important, even in the era of big data, large data sets, et cetera, where it can be difficult, of course, to capture the complexity of data. Nonetheless, some kind of visualization, some summary statistics of what's the typical value, the ranges, and this kind of thing is really essential. And I do this before I touch any kind of statistics at all. Okay. Understanding the data will also involve trying to understand what's the generative model, what's the thing that created your data, or the ideal data. And this may be very, very complicated, and often when this is complicated, this is when we start looking at machine learning kind of tools, because you have more freedom when it comes to the model, because it's kind of defined by the training data in some sense. And very importantly also, think about the measurement or the noise model. This is the thing which ultimately will result in you defining your likelihood, for example, if you're doing, for example, a Bayesian analysis. And I think this is one area where perhaps machine learning and statistics diverge a little bit, in that in statistics you're very concerned about the noise and the uncertainties in the measurements. As Brendan said, it's the high noise to signal regime, right? Whereas in machine learning you're often less concerned about the individual noise, but more about the population properties and how much, the distribution of the data. But whatever you're doing when you're trying to solve a problem, understand the data, okay? And what contextual information do you have, and what do you want to use? So the analogy here was the discussion I brought up about, the priors you have for distance estimation. The contextual information there was, for example, the distances are positive. But how much further do you go down that route? Do you take into effect some kind of model of the galaxy? So this will often drive you to defining your prior. Okay? And in practice, it can be very hard to convert sort of the information you have into a mathematical prior. And there are techniques then for doing things like, trying out different priors and seeing the effect it has on your data. But think carefully about the contextual information. It's data analysis is not done in a vacuum, it's not done in a void, and it is subjective, whether you're talking about priors or not. There are choices to be made, and one of them is this contextual information. Okay. Often problems are very difficult to solve in an ideal, perfect sense, so identify what kind of simplifying approximations you can make. You know, maybe the full definition of the problem is intractable, but a very slight simplification, a very slight approximation will greatly simplify it without really degrading the results very much. Okay. So this can actually be very important. I think this is often part of the black art in doing data modeling, is identifying those approximations which are valid, but which make a great improvement in robustness or speed or just being able to solve the problem at all. And I would say be principled. There's a reason that we use Bayesian statistics, because it has a very solid principled basis. But I would also say be pragmatic about things. Yeah, don't be dogmatic. Don't just use something because you feel that has to be done that way. Yeah, often one does need to be pragmatic to make the difference between a problem which can be solved in theory and a problem that can be solved in practice. Okay. And if there's one thing you want to remember, okay, from everything I've said, it is don't simply pick up a tool that you find online somewhere, whether it's a Bayesian method, a machine learning method, or whatever, and just blindly apply it. Think about the problem. Okay, this is really the most important thing. Go through these kinds of steps, understand what you're trying to do, and then identify the tools you want to use. Okay, so that's really all I want to say. I mean, I'd be happy to talk to people by email if there are questions, etc. Like Brendan, I'd like to thank particularly the organizers for organizing what I think has been a really fantastic workshop. I've really enjoyed it. I've enjoyed talking to you, to everybody here. Some really great ideas. And yeah, I agree the fish was a little bit dodgy last night. But other than that, it's been fantastic. Okay, thank you.
Thank you very much. Thank you.
All right, well, I guess as summary of my day yesterday, I think there were 3 sections which each have about 3 summary points each, which is nice. So the first part, thinking about hierarchical models, I hope that the things you took away were at least that when we're dealing with hierarchical models, we can think of the upper layers of the models, being those closest to the likelihood function, as those containing the parameters which will be most informed by our data, and that as we go down lower to more abstract parameters of the model, these layers receive less information typically from the data and are therefore the most prior sensitive. So that's where we need to think most carefully about prior choice. And when you are building a hierarchical model, it's worth remembering that one of the the most powerful features of hierarchical models is this effect of shrinkage. So think about, does your model in some way provide shrinkage? And if so, in what way is it doing it? And is it a sensible way? And is it the most powerful way it could be doing it? Then specifically when we come to think about prior choice, we'd like to think about priors, or it helps to think about priors in a number of different ways. In the first most natural way is to think about priors as expressing knowledge. And usually this is, when I say it's natural, it's when we're dealing with the upper layers again of the hierarchical model closest to the likelihood. So when we're dealing with parameters which have something more tangible or more physical as an interpretation. So we, in that case, may well be thinking about our priors as expressing genuinely our prior knowledge, say knowledge from experiments or knowledge of the natural world. Also, in model building, though, we need to think about our priors as providing regularization, so helping the model avoid unphysical or mathematically undesirable types of fits, and to limit our exposure to just very noisy data, which makes us make a poor guess. And then finally, when choosing priors, to think about priors in the role that they provide in a Bayesian context of completing the generative model. So if we have proper priors, we should be able to sample from them and sample mock data sets based on those priors. And if we visually inspect or make some other kind of interrogations of those mock data sets, it should help us to decide, even before we see the data, whether we've chosen sensible priors. Does the expected data look like the data we genuinely expect to get? And then finally, regarding the later part of my day, regarding sampling methods, I think the main point to take away was that there are alternatives to MCMC. So MCMC is a good approach. MCMC and Hamiltonian Monte Carlo are great approaches for particular types of models. But there may well be other models, or for example, models containing Gaussian processes, which can be perhaps well approximated in the Inler framework. So you might well favor this type of method. Or for models where data comes to us, say, in a batched way or an online way, where we'd like to make continuous regular updates, or where the data has a natural ordering through time, perhaps, these type of models are very attractive for sequential Monte Carlo methods. And in that context, I didn't go into the available probabilistic programming packages for implementing this sampling in a somewhat automatic way, but there are a number, and one I think which is perhaps the easiest to use and get a feel for is this one called Libby, available at libby.org, and there's quite good documentation of it. And yeah, within this same framework, I didn't discuss it, but Brendan definitely mentioned and has some notes on it. Nested sampling would be another type of way of sampling your data, which is an alternative to MCMC, and is worth considering. Hopefully, the difficulties of installing R in various packages didn't stop you from, or didn't prevent you from trying at least one of the two exercises. And if you do, say back at your local institution, manage to get a working installation of Inler, I hope you can sort of go back through that exercise and for anything that you missed. And if you successfully were able to run the sequential Monte Carlo, or the sort of the tracking example, hopefully you got something that worked a lot like this, and it allows you to see the way that the particle approximation of the posterior, which is in gray, is able to track and follow in this online way the noisy, the true position of the target, which is in magenta, given only the noisy green observation of it and that indistinguishable random field. So that's all, and like the others, I'd like to say thanks to the organizers and for all of you for giving your attention and taking an interest in probability and statistics.
Thank you.
Okay, so we're going to do the tutorial now. You've seen the GitHub link about 10 times, so you should know where it is. I recommend very, very strongly working in pairs. I'm a strong believer of pair coding. And 70 or 80% of people knew Python. For those who don't just pair up with your friend who also doesn't know Python. Find someone who's a good coder and work with them. But I recommend that you each, even if you're working together discussing things, that you each have your own version of the tutorial so that you can come back to it later. So even if you don't quite know what you're doing and your friend is the one who's doing it, follow along and type everything into your tutorial and see how it works so that later on you can play with it yourself. So just quick hands up, who still hasn't got everything working? Who's still having problems? Fantastic. Okay, so we'll go until about 4:30, and then I'm going to close off with some cool slides on deep learning. And in between, there'll be tea.
Yeah. So, when the tea is, when the coffee and the cakes
Tell I'm a tea drinker.
are there, I'll let you know, and you can just smoothly go and get some coffee and cakes and come back and keep working on your solutions.
So you have about 2 hours, yeah. And is there anyone who's been super eager and has already finished the tutorial? I know of one. Cool, super eager people. So for the super eager people, you can do whatever you want, but also in the repository, there's some SDSS spectra. If you want to play with a regression problem, you can see if you can do a good job of predicting redshifts from spectra or whatever you want, if you want to play with that data set. Or there's also a very, very simplistic deep learning tutorial, if you want to go for that. Or you can work on your own stuff and use this opportunity to play with machine learning and ask me if you have any questions. Okay, go for it. We've got about 2 hours. Thanks.